Next up is our Harani and Stavros from Facebook.
Hi everyone, my name is Harani. I'm an engineer at Facebook, and this is my colleague Stavros. We're here today to talk about Scuba, Facebook's real-time and monitoring analysis platform. Let me start with a small story. So on April 14th at 9 p.m., a couple of ad engineers got notified about a drop in ads revenue for Facebook. This can be a very serious issue since even small drops can lead to substantial amount of loss for the company. On investigation, within a couple of minutes, the users were able to correlate this with a drop in ad impressions that were being served. And this correlated with a drop in user engagement on Facebook. Strange. What could have led to this dip in user engagement, especially given that it was a weekend? Does anyone want to take a guess? What event could have occurred on April 14th, which is a Sunday, at 9 p.m.? Yeah. No? Any other guesses? Yes. So yeah, as it turns out, April 14th at 9 p.m. was when the premiere of season 8 Game of Thrones was being aired. So, nice guess. You guys are not sleeping, I can see that. So the alert that notified the user, and later on the entire investigation, like the data that was used for the investigation, was based on Scuba. This is a very good example of how hundreds of teams at Facebook use Scuba for both monitoring and investigating. In order to provide effective alerting, data needs to land in Scuba within a few minutes from when the actual event had occurred. In order to provide interactivity during user investigations, it's very important that we support low latency queries. Since query patterns are very particular to the scenario that's being investigated, it's also important that we support arbitrary query over raw data. This means that data is not pre-aggregated at any layer within the entire system. And this also allows our users to build rich visualizations on the fly. Before we dive into some key components of Scuba's architecture, let's look at how it evolved over the past few years since its inception about 8 years ago. Through this entire time, we had to maintain some key constraints in the system. Few of them are the 2 to 3 seconds latency guarantees and also the 1 minute publishing latency. We started with a simple in-memory row format storage, which offered limited resiliency, and we built custom pipelines for every new use case that we were onboarding. As we grew, memory became quite expensive, and so did onboarding newer use cases. So we moved to a more columnar storage format with support to offload data at individual column level. And we moved to a unified streaming-based ingestion solution that was shared across all our use cases. The third generation of Scuba, which is currently in production, has dynamic load balancing capabilities across the various data pipelines that are ingested. More efficient sharding algorithms, which helped us reduce our storage footprint and also helped in improving query latency. And finally, we moved to a tiered storage model where we are now able to query historical data in addition to real-time data. We are working towards the next generation where we want to combine disaggregated storage and compute architecture to help us scale further in the future. So as you can see, as Facebook grew, we had to support an order of magnitude growth, both in scale and the number of use cases that we were onboarding. Now let's take a look at some of the key components in Scuba.
Now that we saw how Scuba can be used to monitor and investigate the revenue drop at Facebook, let's take a look at the infrastructure that makes it possible to enable that use case, along with a wide variety of other use cases at Facebook scale. We'll start with an end-to-end diagram that shows how data flows throughout the system. With Scuba, we follow a log everything approach. We encourage our developers to log everything they need to be able to monitor and debug their services and worry later about dealing with potentially high volumes of data. We also wanted to make logging simple, so we only support a limited set of data types, and we don't enforce a fixed schema. If developers want to add new fields to their log records, they can do so, and we will deal with schema changes further downstream. We use Scribe, the system that Dino and Christina described earlier, as our transport message bus to collect all the different logs from the entire fleet of hosts at Facebook. That data flows into our Tailor tier, which is where ingestion takes place. A Tailor tier consists of a set of Tailor tasks or jobs that read from Scribe categories, and what they do is they batch raw log records for a few seconds and write them into our internal storage format. Our storage format is similar to Parquet or ORC, so it's highly compressed, it's columnar, and we also contain the schema of the raw log records that we read. The Tailor tier is built on top of Facebook's internal streaming platform. The streaming platform takes care for things like load balancing for us and dynamic scaling so that we can deal with fluctuations in the input rate. It also allows us to quickly deal with outages that potentially can be region-wide by restarting the jobs. And we can also go back to Scribe for a few days to read data if needed. In case of region-wide outages, we run 3 independent Tailor tiers across 3 different regions. From the Tailor tier, data gets constructed and is sent to our Scuba backend. The backend itself is architected as a massive fan-out tree architecture, and the data is stored on the Leaf storage nodes as a single copy on local flash. So that means that Scuba can be a lossy system. And to deal with that loss, whether this is temporary or permanent, we keep a validation service where we count how many rows we inserted on each table. And we also run our backend tier again into 3 different regions. So this is the backend, and the way we access the backend, our users access the backend, is through a dedicated Scuba UI. This is a UI that contains a Visual SQL query editor and offers lots and rich visualizations. But this is not the only way that users interact with the system. In fact, the majority of the queries in our system come through our SQL API. This is used by other services at Facebook to build tools on that. You saw an example of another service earlier today when Helga talked about comparison view. 2 of the largest workloads that we carry at Scuba is our real-time monitoring dashboards and one detection, which is our internal way of running automated detectors. So now let's dive a little bit deeper into the Scuba backend and see how queries are getting evaluated when they go to the backend. The entry point is what we call the edge proxy. This is responsible for maintaining a persistent connection with the client, and it also forwards the query to all the 3 regions out of which we run the Scuba backend. Once the query is within one region, it hits the origin proxy. This is a place that we perform workload management and admission control. Scuba is a multi-tenant system, which means that it executes queries from a wide variety of use cases. Those queries can be small, big, expensive. So we want to make sure that we have queues and give higher priority to those queries that need it. We also want to make sure that we can block potentially misbehaving sources and queries and blacklist them. This is what happens in the origin proxy. Once the query passes the origin proxy, it reaches the root of the aggregation tree. From there, it will get propagated through one level of aggregators to the Leaf nodes, which are our storage nodes. I said before that the storage nodes are self-contained because they contain the schema for each data block. So what we do is we perform a local evaluation of the query on each storage node, and we have implemented really efficient vectorized SQL processors to perform filtering, projection, and partial aggregations. If a node is down or not responsive, it will simply not evaluate that part of the query. When the nodes are done, they're going to start propagating the result to their parents. So while queries flow top-down, the results and the data will now flow bottom-up. They will go through one additional level of partial aggregation. This is the aggregator level. And then finally, the root is going to collect all the results from the aggregators, and it is going to do the final aggregation. From there, the result is going to be sent back to the edge proxy. And this is the place where we are actually going to compare the 3 different results that we got from the 3 different tiers. This might be a little bit different because of outages or hosts that may be overloaded, that have timed out. So we're going to use a validation service that I mentioned before to pick what is the best result and send that back to the user. So next, let's take a look at what are the key enablers that make it possible for Scuba to perform really fast ingestion and really fast queries. For us, Scribe is a key enabler because not only it gives us a single uniform way of receiving data, it also lets us do recovery by going back in time if we need to. We're not going to talk more about Scribe. Dino and Christina did a great job explaining Scribe. So we're instead going to focus on the design trade-offs that we had to take to make Scuba possible. To be able to support a wide variety of use cases in a centralized manner, we had to be really opinionated about what Scuba does and what Scuba does not do. We also had to be flexible in the way we deal with data and in our data expiration policies so that we can deal with this high volume of data. And finally, the 4th enabler for us is the platform features we had to build so that other services can leverage Scuba and use it to build tools around it. So let's take a look now at the design trade-offs.
So let's look at some of the features that we built and some that we had to actually give up in order to enable fast ingestion and even faster querying. We have caching at multiple levels and multiple layers in the system, and this helps us avoid refetching and recomputing data. Since a query tries to scan the entire data set within the time range, caching is really a critical part of our system to avoid high latency across similar queries. Queries follow a typical leaf aggregator architecture, and leaf nodes don't communicate with each other. This again is for faster querying, but means that today we don't have any sort of joins or global sorting on Scuba. So we don't store any kind of indexes, sort keys, or distribution keys. This again helps for super fast ingestion, but we do have zone maps on time columns, which helps us with efficiently pruning older data. We have a simple flat schema, and we have support for primitives and arrays, but we don't have any support for natively nested data today. And finally, data is distributed across a large number of machines for each of our use cases and is replicated across multiple regions. But we don't guarantee any consistency across these replicas, which means that data availability is best effort by design. This again is for both faster ingestion and querying. Because Scuba was basically built for real-time analysis, deletion is a central part of the system. Today, we do pruning on an hourly basis, without which we would run out of space within 24 hours. We also allow our users to configure flexible retention policies for their use cases. Today, a user can configure retention based on both time and space on the entire table or a subset of columns in the table. They can also have subsampling enabled at various points in the system, like at logging or during ingestion or once finally the data has been written and stored. So alerts and detectors are by far the largest workload that we support by query count. And this is enabled through a time series cache that's built on top of Scuba's platform. We also support sophisticated anomaly detection queries. For instance, in the example here, today we can easily detect the violation outside the anomaly bands automatically without the user having to pre-configure thresholds and notify them. We also have a huge support for custom visualizations on top of Scuba, what we call as presenters. These are easy to extend, and users always use them to build newer services on top of Scuba. Let's look at a simple use case where we are using a few of these presenters. Yeah, this is a case study of how we utilize presenters for investigating inefficiencies in code bases. Overuse of shared pointers is a common inefficiency that we see in code bases today. But there can be a long tail of places where we could optimize. So how do we figure out which ones are actually worth fixing? So we have a data set in Scuba today that collects sample stacks traces from all the machines in Facebook. We could simply filter by a function name, group by the service name, and order by the number of machines and the amount of CPU that's being used by the service. So for our particular example, to identify shared pointer usage, it's usually characterized by a high usage in atomic adds. So we try to group by atomic add as a function name, and we're able to identify like the top services that we actually want to optimize. Great, so now we found the service name, but how do we actually find the code path that is actually leading to this usage? We use what is called as icicle view or flame charts for which help us in understanding how much CPU is being used by each of the function calls and stacks. And for our example, it's pretty obvious from here to see that atomic adds is being invoked a lot by function X, for example. And finally, once we have fixed the issue, we can use time series view on Scuba to see that it actually helped in dropping the number of CPU cycles that were being used by this particular function in this service. On that note, let's look at what is in store for Scuba in the future.
So hopefully by now you have a good idea of what Scuba is, how it works, and how we use it at Facebook. For the rest of the talk, we wanted to share with you what our current plans are for what we're currently working on Scuba and what some of our plans for the future are. So today, Scuba is used at Facebook to access real-time data. This is data that can become available within a minute, but it also has limited retention because we can't keep it in Scuba for a long time. For historical data, or data that we want to keep longer, but we can afford waiting for a few hours to make their way into the storage, we use Presto. Presto is an open source SQL engine developed at Facebook, and we use it as a SQL engine to access our warehouse storage. Our warehouse storage is a Hive-like storage solution, and that can store also the same data sets that we also store in Scuba, but it won't have a real-time information. Presto can also do complex query processing. It can do joins, it can do complex aggregation, something that Scuba cannot do. So as you can guess, one of the biggest asks that our users had was how we can integrate those two systems, how we can give them access to both real-time and historical data, and how we can let them do complex operations on those data. So what we did this year is we integrated those two systems in a bidirectional way. The first direction is from Scuba to Presto. The way this works is the following. When a user goes to Scuba and they want to query a dataset, let's say that they want to see a time series chart that goes back 30 days, but we only store 1 day worth of data in Scuba. What we will do is we will display immediately the 1 day portion of the time series chart, and in the background, we're going to fire a query to Presto. When that result comes back from the warehouse storage, we're going to actually stitch it with a Scuba result and then refresh the time series chart, and then you can see the entire time series for the 30 days. We also did the opposite integration from Presto to Scuba. The way that works is that a query hits Presto, and from there, it's been sent to Scuba. In fact, Presto connects directly to the storage nodes of Scuba, treats it as an external source, and can efficiently retrieve data from there by pushing down predicates. Once the data gets retrieved by Presto, it can join it with other data in the warehouse and do complex processing as well. So this has been working well for us, but we wanted to take a step further. And this is how we also started thinking about the fourth generation of Scuba, which follows a disaggregated storage architecture. What we wanted to do there is to stop thinking of data as real-time and historical, and instead be able to ingest data directly into the warehouse storage in real time so that we can keep it as much as we want, rather than having limitations of Scuba storage. Not only that, by doing this, we also let other compute engines that we use in Facebook to access that data. To do that, not only we had to think about how to decouple compute and storage in Scuba, we're also thinking about two additional components that we have to provide. One is how to combine the real-time and batch ingestion to the warehouse, and also how to provide those aggressive and proactive caching techniques so that we maintain the real-time aspects of Scuba and the low latency querying. So this is what we are currently working on, and on the infrastructure side of Scuba. We would like to end the talk by giving you a glimpse of how we are thinking about Scuba and observability at Facebook. Scuba today is used as a centralized place to efficiently ingest, store, and query structured logs. We are also working on making or on supporting machine logs or machine data or unstructured logs in Scuba. But if you look at metrics and traces and what systems we use to store them in Facebook, we have separate systems. Metrics are stored in our internal time series database and served by a system called ODS. And traces are handled by a system called Canopy. Today, there is no way to go from one system to another and be able to associate, for example, a trace with logs that may have been recorded at the time the trace was being taken. This is exactly what we want to do in the future. We want to be able to record the information that shows us which records and which logs were being recorded at the same time that the trace has been happening, and also which metrics were also being recorded. Once we have that information, we want to be able to jump back and forth across the systems and enable richer investigations for our users. And with that, I would like to thank you for your attention and invite you to ask questions.
Thank you, Harani and Stavros. I have an anxious questioner over here. Microphone is on its way. And I saw one in the middle over here somewhere that's next there.
Thank you. So I have a question. I mean, I fully understand why you kind of made the design compromises in terms of like the Scuba, in terms of the lack of ability to have global joins and so on. My question is, how is that actually circumvented once you go through Presto and you support like full-on query semantics? To be more specific, how do you avoid situations where you can have like a crazy join that's going to end up hitting like 1,000 by 1,000 nodes and just take your system down once you have like 1,000 such queries in your system?
Yeah, so the question is, if we are going to go through the effort of doing joins, and we do that through Presto, how do we guarantee that then we might preserve low latency queries, or if I understand correctly? So that's a good question. The way we think about these use cases are actually we're thinking that there are separate use cases. There are analytical use cases, like use cases for analytics, for ad hoc analytics, where the users actually don't mind waiting a little bit about the results. So the expectation is that if you are issuing a multi-way join query that might touch both real-time and historical data, then you're going to get current Presto behavior. That's why in today's iteration, we had both directions. We wanted to make clear that if you go through Presto, you should expect a Presto experience, but if you go through Scuba, then you should expect a Scuba experience and see the results coming back really fast. The other reason that we didn't want to go in the way of integrating joins inside Scuba was that we didn't want to alter the nature of Scuba and affect other queries by making them slower. And we already had a really good SQL engine at Facebook, which is Presto, so we didn't want to re-implement that.
Okay, so just a quick question. So Presto has like full SQL semantics and full SQL query optimizer and everything under the hood. Scuba doesn't. Is that kind of the separation right now, the way things are designed?
Right. You can think of Scuba as a really thin SQL processor that does single table, fast projections, filters, and aggregations. But those are, if you need, these are approximate aggregations, right? You cannot do like a global sorting.
Okay, and sorry, just to kind of finalize on that, how do you make sure that your Presto queries are actually not killing out the experience of the Scuba users? How do you make sure that Presto query is not going to kind of take down your the Scuba execution?
So the storage layer, yeah. So we route, as I think Stavros mentioned, through the query routing process. Like we have queuing at our local proxy layer, and we have sort of admission control and everything built at that layer. So because Presto, inherently we assume that the user has expectations that it's going to be slow. The queue sizes and everything that are defined for volume through Presto is very limited compared to the rest of the volume that comes to Scuba.
Thank you. Over here.
So it sounds like structured events are parsed, flattened, mapped to a columnar store. If that's the case, how do you handle explosion and cardinality for keys? Things like field names that are in and of themselves UUIDs, things like that.
So the short answer is we don't. We just have a limit on the maximum number of columns we are going to generate. So that protects the system and our users from a misbehaving source. But once you reach that limit, if you really need to have those fields, the way to do it currently is by including them in a JSON string and then be able to process that JSON string later.
Yeah.
Thanks for the question. Did you have something to add?
Yeah. So we have like customized UDFs that even users can build on top of our platform if they want to like parse the JSON and have like nested sort of query capability, right? So.
Thanks. Right here.
Yes, you started your talk by saying that there was a dip in ad revenue on April 14th evening. So can you give a high-level overview of like how you found out the issue using Scuba? I mean, I understand like what you're doing here, but what is less clear to me is like how do you put these two together to find out the root cause analysis for that?
Right. So probably at some point the ads engineer would have like created an anomaly detector on top of this chart that I had shown. They may or may not have configured any thresholds really, but we have like detection algorithms that are running continuously, and any spike outside the anomaly range automatically notifies the user that might have like tagged that chart.
Time for one more. Over here.
Thanks. With data at that scale, is there a general assumption that everybody can see all that data and anybody can query it? Or is there entitlements, and how do you handle those entitlements at that scale?
That's a great question. So while we mentioned that there is no centralized catalog in Scuba and that data and schema is self-contained within the storage nodes, that's not true about our ACLs and how we let people access data. That actually we're integrated with the Hive metastore, and we use the same semantics and access policies that the warehouse data uses.
Great. Thank you, Harani and Stavros.
Thank you.